Okay, this chapter is chapter 10 on thermodynamics. We're going to look at relationships between heat and work and then the first and second law of thermodynamics. So today, imagine a small balloon filled with air at room temperature, and suppose you're holding the balloon in both hands and you squeeze it to a smaller volume. Has any work been done? Think about back to what the equation for work is and think about, has any work been done? Has heat been transferred into or out of the balloon? And then has the internal energy of the balloon changed? Think about those three questions. We'll answer those throughout this section. So imagine pulling a nail from a piece of wood. Is this work? And we'd say yes, because the equation for work, if you remember, work is equal to force times the distance. So you're applying a force to the nail, it's moving across the distance, so yes, the nail did do work. And since work is done, the energy of the nail must be increased. And which way is it increased? Well, the internal energy is greater, and so the temperature increases. If you feel the nail after you pull it through a piece of wood, it does feel a little warmer. So the internal energy of that nail has actually increased. So what will happen to the internal energy of the nail over the next few minutes? Well, we'll go back to the original energy, and it has released what we call heat. We release that internal energy in the form of heat. So that's another type of energy that can be released or gained. So now imagine placing a balloon over a flask with some water in the bottom, and after doing so, you put that flask over a flame. So is heat transferred? Okay, yes. We know it's the flame obviously gives some energy to the glass and to the water. So how's the internal of the water affected? It increases because the temperature is increasing, and the water then changes into a gas. So is work done? And we would say yes. The steam is expanding and it's moving the balloon, so it is moving it across the distance, and the air outside is being pushed away. So yes, work is done. So heat and work are both energy transferred into or out of a system. So the system is the particles that you're choosing to study, so the hammer, nail, and surrounding air, and the flame, flask, water, and balloon and surrounding air would be the two systems that we looked at. So a gas, we have another equation for work that is based on the volume change. So work is equal to pressure times the change in volume. So work is positive if delta V is positive, the volume increases, because remember that the delta V would be final minus initial. So if we have a larger final volume, that would be the volume is increasing, then work will end up being positive. It's going to be negative if our final volume is smaller, or if the volume decrease, then the work is going to be negative. You can think about, is work being done by the system or is work being done to the system? So you can also think of it that way. So here's some different processes, and they have specific names. An isovolumetric process is when work is equal to zero because the volume never changes. The energy may change and heat may be exchanged, but the volume, there's no work done. So the Bohm calorimeter shown below uses an isovolumetric process because the walls are rigid. So you are not changing the volume of that system, even though you're adding heat into it, you're building up pressure. And so you're still doing, it still has, the internal energy and the heat has been exchanged, but there's no work done because the volume has not changed. An isothermal process is when there's no change in temperature. So work may be done and heat is exchanged, but there's no change in temperature. So a balloon undergoing a gradual drop in pressure is isothermal because it absorbs heat to maintain a constant pressure. As the pressure drops, the balloon expands and starts to cool, but the heat enters from the outside air to maintain the temperature. So it's a slow enough change that it does not change in temperature as the work is being done. An adiabatic process is where no heat is transferred. So Q is 0, but internal energy may change and work may be done. So filling a balloon from a helium tank is adiabatic because the balloon fills so rapidly, no heat can enter or leave the balloon. So this time it's fast work done instead of slow like the isothermal. Very rapid processes are almost all nearly adiabatic. Okay, so let's watch this video on those three processes, and they are going to compare those three.
Is always from a warmer object to a cooler.
Let's start that over.
The natural flow of energy as heat is always from a warmer object to a cooler object. In a refrigerator, the opposite occurs. A refrigerator does work in order to transfer energy from a low temperature region inside of the refrigerator to a high temperature region outside the refrigerator. A refrigerator contains a closed circuit of tubing filled with a liquid known as refrigerant. Let's start with the refrigerant at this point. It is in a liquid state at a low temperature and pressure. It is colder than the air inside the refrigerator. The refrigerant absorbs energy as heat from the refrigerator's interior and lowers the temperature of the items in the fridge. The transfer of energy to the refrigerant increases its temperature and causes the refrigerant to boil. By the time it reaches the compressor, it is a gas at moderate temperature and low pressure. The compressor does work on the gas while compressing it. No energy enters the gas as heat, so this is an adiabatic process. The compression increases the pressure, internal energy, and temperature of the gas. The gas is pushed into pipes that are mounted on the back of the refrigerator. The pipes are exposed to room air at a lower temperature than the gas, and therefore the gas transfers energy to the outside of the refrigerator. As it releases energy to the room, the gas cools and condenses back into a liquid. The high-pressure liquid then squirts through an expansion valve. Its volume increases. While expanding, the gas does work on its surroundings. Its internal energy decreases rapidly. It is now at a low temperature, again ready to absorb energy from the inside of the refrigerator.
Okay, that was a really good explanation how those refrigerators work and how the energy flows. Okay, this video is now on the combustion engine and how that works with the ideas we just talked about.
Combustion engines convert chemical energy into work energy. Let's consider the 4-cycle gasoline engine found in most vehicles. During the intake stroke, the cylinder descends, taking in a fuel-air mixture from the fuel injector or carburetor. Then, in the compression stroke, the mixture is compressed. This raises its temperature and makes it easier to ignite. A spark produces combustion and begins the combustion stroke. This is when the engine is doing useful work. Now the chemicals are burned up and need to be removed. This is done during the exhaust stroke. Then the cycle is ready to begin again. 3 of the 4 cycles of this engine are just housekeeping. Only the combustion stroke involves an important transformation of energy. In this stroke, the chemical potential energy of the gasoline is turned into mechanical work.
Okay. So now, what do you think? So imagining a small balloon filled with air at room temperature, and you're holding the balloon in both hands and you squeeze it into a smaller volume. Has any work been done? I would say yes. Has heat been transferred into or out? And has the internal energy of the balloon changed?